Hey there, stats students. Welcome back. We're going to finish up section 12.1 today, talking about inference for linear regression. So yesterday we went over how to do a linear regression t-interval on your calculator, and then it gives you the interval and the slope from the sample, degrees of freedom, and so on. Today, though, we're going to look at performing a significance test for the slope. So if conditions for inference have been met, you can use the slope from the sample B to construct a confidence interval for the true population slopes regression line. But you can also do a significance test. So you can test to see if a specified value is plausible for your true population slope. So the null hypothesis has that same general form, but we think that our parameter here is beta, and that is the true population's slope. So in order to do the test, you need to standardize your sample slope using the statistic minus parameter divided by standard deviation of the statistic, and our statistic is B, parameter is the null hypothesis value for beta, and the standard deviation of the statistic is that standard error of beta. And then to find the p-value, you use a t-distribution with n-2 degrees of freedom, and that's the t-test for slope. There it is. So there is our, believe it or not, final inference method that we're going to learn this year. Yay! This is called a t-test for the slope of a least squares regression line. So here's everything you need for it. Conditions, we've talked about it. There's 5 conditions for this one. You've got a null hypothesis. Your test statistic is given by that. And it could be a one-sided greater than test. It could be a one-sided less than test, or it could be a not equals test, which would be a two-tailed test. And of course, you can do this on your calculator. I have the data typed in for the non-exercise activity and fat gain into list 1 and list 2. You can see, this table typed in here for list 1 and list 2. So what I can do is I can go to stat and then test, and then it's towards the bottom of the list. This is called the linreg t-test, option F here on my calculator. So I can run that. My X list is list 1, Y is list 2, I leave frequency as 1, and then you have to decide what type this is. For this question we were answering with this data, it was a not equals test. We wanted to see if it was possible that there was a linear relationship, which would be which would mean that we're testing to see if beta could be 0 or not. And then I'm going to store my regression equation in y1, and then I hit calculate. And so these numbers that it gives me here, this is the test statistic, this is the p-value, and notice it's got an e-4, which means it's, times 10 to the -4th power. That's a very small number. Degrees of freedom 14, and then there's the y-intercept of the sample, there's the slope of the sample, there's the standard deviation of the residuals, and then there's r squared, and there's r. Now, if you compare the values that I got there with this Minitab regression output table, we're going to learn what 2 more values on here mean. So yesterday we talked about what this number means. This is the standard error of our slope. But this number you'll see matches this number right here. That's the test statistic. And then this number right here, under the letter P there, that one matches this number. Now it doesn't quite match, but keep in mind that this is times 10 to the -4th, which means, slide the decimal over and you'll get approximately 0.000. So that's how you can use your calculator to get your test statistic and your p-value for this type of test. All right, let's take a look at an example. Infants who cry easily may be more easily stimulated than others. So this might be a sign of a higher IQ. Now, child development researchers explored the relationship between the crying of infants from 4 to 10 days old and then their later IQ test scores. So what they did is they took a rubber band and they gave a little snap on the sole of the foot that caused the infants to cry, but didn't really harm them other than that. And they recorded the crying and measured its intensity. And then they later measured the IQ at age 3, and this table contains those results. So when you see a big table like this, I'd like to give a word of caution, and that is, don't just start typing the data into your calculator. Read the question first. Now, there's often times where they're going to give you additional information that makes it not necessary to enter all the data in, and this can save you valuable time. So, if you look at the information we get in the actual question, we are given the following. Here is the scatter plot, and here is the regression analysis output table. Now with this information, we can answer this question without having to type it into our calculator. And that question is, do these data provide convincing evidence that there is a positive linear relationship between crying counts and IQ in the population of infants? So this is going to involve a significance test, which means I need to start with my state. We're going to use these two hypotheses. So the null hypothesis is that beta equals 0. The alternative is that beta is greater than 0, and that's because of the way the question was worded. We actually did have a direction in mind. This word positive right here means that we think it goes up. As this number gets bigger, so does this number, is what we're trying to test as our alternative, and that would indicate that we're testing to see if the line has a positive slope. So that's the alternative hypothesis, is that beta is greater than 0, which means the null hypothesis is that beta is 0. But then I also need to define the parameters here. So this is beta is the true slope of the population regression line relating these two variables. That would be crying count to IQ score. Since we didn't have a significance level that was given to us, we're going to use a significance level. Alpha is 0.05. Then plan. So the name of this test, the inference method is called a t-test for the slope, beta. The conditions then next. The conditions next then we need to check. There are 5 conditions. First is L, that stands for linear. So we can just look at the scatter plot and say, okay, does it look like a linear trend overall? And the answer is, yeah, it does. And then we can also look at the residual plot right here and say there appears to be a random scatter above and below 0. So that suggests a linear model is appropriate. Next, the independent condition. So, IQ scores of individuals should be independent, so that's fine. And then because we're sampling without replacement, we check the 10% condition. And yes, it seems reasonable that there are at least 380 infants in the population. Next is N, that's the normal condition. So we don't look at this or this. You can use either a histogram of the residuals, which we do not have, or you can use this normal probability plot right here. So this is what I'm going to look at. There you can see is a slight curve. So a lot of it's linear, but then at the tail here, it looks like there's a curve right there a little bit. So that does cause slight concern, but you can see it's only because of kind of these 2 points. Now this might suggest that the responses may not be normally distributed about the line for each x value, but with such a large sample size, n is 38, the t-procedures are actually quite robust against departures from normality, so we are good to proceed. LINE is equal variance, so I look here and I look for kind of equal spread at individual x values, so like what's the general spread around it. I can see, yeah, there's like 1 point up there, but that's just 1 point, so this doesn't really give me cause for concern. And then random, we were told that these 38 infants were randomly selected, so that condition is met. Now, in the do portion, because I'm given this table right here, all I have to do is look at this number and say that's the value of the test statistic. If you look at, the slope goes right there, our null hypothesis is 0, the standard error right here, if you divide, you will get that 3.07. Now, the p-value, though, the p-value for this test is actually not going to be 0.004. That's because that p-value that's given right here is for a two-sided test. Now, so all you have to do, though, is take that value and cut it in half, and our p-value is 0.002. So now all these numbers I've circled in blue should be numbers that we know how to interpret, and the numbers I've crossed off are numbers that we're really not going to use when we look at output tables. By the way, just a reminder, y-intercept, slope, standard error of slope, test statistic for a test of the slope, p-value for a two-tailed test of slope, standard deviation of the residuals, and that's r squared. And then because our p-value is much smaller than 0.05, we do have enough evidence to reject the null hypothesis, and we are able to conclude that there is a positive linear relationship between intensity of crying and IAQ score in this population. All right, next. Final example here. Our bodies have a natural electrical field that is known to help wounds healed. So how does change in the field strength affect healing? A series of experiments with newts investigated this question. In one experiment, the two hind limbs of 12 newts were assigned at random to either experimental or control. The electrical field in the experimental limb was reduced by 0 to applying a voltage, and the control limbs were left alone. Researchers then measured the rates at which new cells closed a razor cut in each limb in micrometers per hour. So, an examination of the data suggests that conditions are met, and then a 95% confidence interval for the slope of the true regression line predicting healing rates when exposed to zero voltage from healing rates in the limbs with normal electrical fields is given by this, negative 0.42 to 0.72. Now, based on this interval, what conclusions should we draw from a test of beta equals 0 versus the alternative of beta does not equal 0 at the significance level of 0.05? So, hopefully, you know how to look at this interval and you know what you're looking for. Because this is a 0.05 significance and a 95% confidence interval and a not equals test, all you have to do is look to see if 0 is this interval or not. Because 0 is in this interval, that tells us that 0 is a plausible value, which means the test will not reject 0. So because 0 is a plausible value, at the 0.05 significance level, we would fail to reject the null hypothesis. All right. And so then we do not have enough evidence. We have insufficient evidence of a linear relationship. So that's it for section 12.1. Of course, let me know if you have any questions or if there's anything I can help with. That's it for today. Cody out. Make sure you hit that like and subscribe.